to the last presentation for the day on RPWS and Langmuir Probe discovery highlights by Jan-Erik Wahlund.
Okay, you hear me? Yes, good. So the Langmuir Probe was one add-on system during the proposal process, actually, to RPWS, with the main goal to measure or map the ionosphere of Titan. But we did a lot more over the years. So I will be Langmuir Probe focused. So if I have missed some references, it's because they don't use any Langmuir Probe data then. But the instrument survived for, well, the whole mission flawlessly and worked very well. We were basically continuously on measuring the plasma density, most of it. You see the system there. We have the probe at the end, and then a guard and a boom, and then a tripod system there where also the search coil was mounted. Okay, so here we have, it's already become history. Of course, the flight spare is now at the Stockholm Museum of Science and Technology. So you can go there and look at it. But basically, it's only a 5 centimeter diameter probe, metallic, a guard with the same potential as the probe, and then sits on a boom like this to get away from the spacecraft, so we can measure the spacecraft potential, basically. We see the Lennart Åhlén here was the main engineer in action. He's unfortunately no longer with us. He was testing some Rosetta probes, I think. Okay, very shortly, you put the probe on a potential, you vary the potential from minus to positive, you sample ions and electrons to the probe, and then you measure the current to it. Rather simple in principle, but difficult to implement as an instrument. By doing this and fitting the curve, you can get many parameters. The most important ones are the electron density and the electron temperature, the floating potential, which you can calculate the spacecraft potential from, averaging over the spacecraft, and then the ion flux. And if you know the electron density, you can derive the ion drift speed. And then we can do this very fast by just putting at one specific potential, and then you get a very fast measure of the electron density variations. So in principle, this is a weather station for electrically charged gas or plasma, thermal plasma. Okay, so here it started. And you see Philippe here, and he's the only one who haven't changed the appearance, it seems. But you see some guys here younger. But what on earth is this guy doing here? He's a PhD student from Sweden wanting to have a system on board, and he's in the proposal team here in 1991. I think it's me. Anyway, as it is, I had read the announcement of opportunities for Cassini. So I went to my made a crude proposal and went to my 2 professors, and they were kind of negative and dismissed me. What happened was that this guy, that's Lennart Åhlén, the engineer, he happened to be at Lesia here in Paris and happened to meet 2 of the engineers from Iowa. And he came back and said to me, maybe. So we kind of went to one of the professors, and he was maybe, the engineer was more diplomatic than me. So the professor said, okay, we go to Iowa. And that's the professor. Okay, so that's why we came into the proposal team, and we have now a Langmuir Probe system, or had a Langmuir Probe system on Cassini. First, the results, Titan. And it was very interesting to be in Jet Propulsion Laboratory on the first Titan flyby, October 2004. It was fantastic to see that the Langmuir Probe system worked and that we got, during the first flyby, a very good account for the Titan ionosphere. You can see Baptiste here, Andy Nagy, Bill Kurth, Scott Bolton you have down there, Caroline Porco, and Jean-Pierre. And I wrote my signature on one of these pictures. I guess, I hope this picture still is around. Anyway, we could map the ionosphere. We did that task. So here you have altitude versus solar zenith angle for Titan. This is solar ionization, photoionization. And then you see some other ionization on the night side, which is energetic particles from the magnetosphere of Saturn. And that probably exists here also, but it's dominated by the photoionization. Also here we get the temperature and profiles. And at the bottom here, it's actually, we measure electrons at the room temperature, basically. It's very close to the noise level also, but we made this. Okay, it became complicated because there was negative ions there and there was aerosol charged, and we had to refine the analysis, but we did that. So we can measure the positive ions, the electron densities, but also the densities of negative ions and the aerosol that is charged. And we compare that with the model with the aerosol precursors, put it in here, and it basically matches the negative ion densities here. This is a work from Lavas. Okay, good. We're in business. So we could then do the solar zenith angle with positive electrons, electron density, positive ion density, and the negative species. And we estimated sizes of these kind of negative particles on the average of a few nanometer radius. Okay. Enceladus and Plume, we also did a lot of measurements of. And here it was really the charged water clusters or grains coming from the Plume that we could start to infer. I think I skipped that one. We know the Plume and the E-ring that is created from the Plume. And here we have the Enceladus 3 flyby. We went right through the Plume, but we also detected a wake behind Enceladus. And you have electron depletion there, but we also had electron depletion in the whole of the Plume. And these electrons were attached to grains. We could say that because we also had the measurement of the ion density. So electron depletion, and also we saw a slowdown of the ion drift speed here. So we had mass loading clearly of the magnetospheric plasma. And here we see if I can, yes. So a density here, and we have a magnetic field there for all the flybys. You can really see the pileup of the magnetic field when you have high densities, and you also can see the wake behind of electrons. So something is eating the electrons behind Enceladus. And further analysis gave at hand that it must be part of the E-ring dust is actually eating the electrons behind here. So you have a kind of a dust plasma wake. You have dust plasma interaction in the Plume because it's nanograins with negative charge, and there are so many of them that they are in a collective plasma together. The dust and plasma is together a kind of a fluid. And that means it's a very heavy plasma. So it's maybe 3 orders of magnitude heavier than a normal plasma, and that's why it's slowed down to a large degree. Okay, magnetosphere measurements we did basically all the time. So here we have ELS measurements in the magnetosphere. together with the Langmuir Probe density data using the spacecraft potential. So we use basically the whole spacecraft as a sensor, being in equilibrium with the magnetospheric electrons, and by so measuring the density, and it works out very well. And we can even measure when ELS is not measuring. So we see the plasma magnetopause here, for instance. We see the periodicities of the Saturn radiation and the plasma disk moving up and down. Sorry, plasma sheath moving up and down. And you can see the sheet is bent up due to that the solar wind is coming from a little bit below. So you can see this. So we were on basically all the time and measuring the plasma density. Okay, in the inner plasma disk, yes, 5. We could see the plasma density was enhanced near the Enceladus moon, but we also could see the plasma were not co-rotating, the red line, and it was not a Keplerian, but was somewhere in between. So it was slowed down. So it was a co-rotation breakdown occurring here. We could also measure the temperature of the plasma from 0.5 to maybe 4 eV at times. We also had the ring dust measurements. We had a couple of flybys in the Janus Epimetheus ring region. And you can see, really see here ion density increases, and you have rather depletion of the electrons in this region. You can see the micrometer size dust hits here, and in all regions where we see dust, for some reason the electron temperature is increasing. We don't know why. And here you see a similar thing for the E-ring, where you have the ion densities increasing, electron densities going down, meaning you have negatively charged dust there. And then you have the corresponding RPWS dust measurements as a form of broadband emissions. The last one here is the Saturn ionosphere measurements. We had 22 proximal orbits, and a few of the last ones went down actually to the ionosphere proper. This one have already been shown. So you have dust coming down in the equatorial region of the ionosphere, and there we pass. So we have done, there's a problematic because it's 34 kilometers per second you pass. So you get a lot of stimulated electron and ion emissions. But we have managed to correct for that. And if you see the upper part here is actually 4 independent measurements of the plasma density. You have the INMS in red here, density, you have the Langmuir Probe densities, and you have the density of the plasma wave emission data, and also our own Langmuir Probe ion density measurements. And they agree for 11 profiles within a few percent. That's amazing, 4 different measurements. We were so happy. There is a lot behind this. I'm not going to go into detail. This is the H3 plus densities, and the green you see here is the H plus densities. But down here, you have a discrepancy between the electron densities, which are measured with 2 methods, and the ion densities from the Langmuir probe. So INMS had a problem because they could not measure about 8 atom mass units. So the difference here is due to that you have water and organic ions, is believed. And for some reason, the electrons are kind of bite out here. And we believe there is a dust component here that eats these electrons. And you have this dust coming down here. This dust becomes charged rather fast, negatively, and then it becomes kind of stuck by the near horizontal magnetic field because it's magnetized. And then they create these kind of layers maybe go ongoing further chemical processing. So this is from this year published. Norway. So lessons learned, and this is end. Collaboration between US and European instrument teams is really got us together, I think. RPWS is a multinational team. One can do a lot with a small instrument contribution, more than you think from the beginning. Long-term projects need to involve young persons up front, and you need to have continuous support even in the science phase afterwards, because these PIs might not be their bosses and other things. The Huygens landing, I took care of the public outreach activities in Sweden. And I must say, I have never become so famous for something I didn't do. So it was a very good public outreach event, though. Anyway, without Cassini, Huygens, we would never have had use, which we have now, and I'm a PI on use, and I know the problems a PI have. And the next project is the ESA L4 mission to Enceladus. And when it reaches there, I'm probably dig down somewhere. But I am promoting the young to go for it. And there are room for RTGs for those who want to give the mission. That would help, I think. So thanks of all of the Cassini team and from our LangMi Probe nerds. Thank you very much.
Thank you, Jan-Erik. Any questions? While you think of the question, I have a question. You saw at the beginning on Titan a very nice comparison of the results among a large number of flybys. Yeah. And you had the temperature, the electron temperatures.
I did.
And they had some spread. And my question is, if there has been any comparison with the corresponding results from INMS about the temperature variability of the upper atmosphere and how it correlates with the electron temperatures.
Oh, we are on the hotter side for the electron temperature, even though it's room temperature for the lowest part, which is the one to compare to, I guess. And but we are very close to the threshold of random electron emissions. So that is 0.015 eV. We have a kind of hard limit which we have measured in lab. It's near this limit, so I cannot say for sure if it's colder or not in the bottom here, but it's cold. I mean, we are measuring electrons on room temperature. It's rather good idea.
Any other questions? If not, let's thank Jan-Erik one more time. And before we convene for tonight, Tina would like to give us a few words.